We're going to continue talking about stability of systems, and specifically go back to Daisy World and talk a little bit more about the switch there from instability to stability. So this is an instability example. And we're going to just talk about white Daisy World. Keep it simpler. So let's just review a little bit about Daisy World. So I've chosen just white Daisy World only, and we'll run the simulation here. Okay, so what happened over time was normally due to solar forcing in this model, the solar flux is increasing. However, with daisies present, if you didn't have daisies, the temperature of the surface would just get higher and higher. But there's white daisies around, and they have an albedo that is larger than the ground, and their presence stabilizes the temperature of the planet for a long period of time until at a certain point they no longer survive and the temperature spikes. Okay, so we described that there is, for most of the model, there's a feedback loop where the presence of white daisies, so this is review, white daisies. The presence of white daisies affects the albedo, which causes the planet's temperature to go down. So when there's more white daisies, the planet temperature goes down. So as we pointed out in the last lecture, if we were to plot these things, white daisies, temperature of the planet, so white daisies high, temperature low. Few white daisies low, temperature would be high. Okay, so that has a negative slope. And so this is another way of thinking about what sign we associate with this. Okay, so if the planet's temperature goes down, white daisies, we said they like it hot. So if the planet of the temperature goes down, the number of white daisies will go down. So that's a positive feedback, because it would work the other way too. Okay, so together, that's a negative stabilizing feedback. So if we look at the parameters here for daisies, we see a temperature tolerance. So their ideal temperature is 22.5 at the moment, and they can grow in a range plus or minus 17.5. But what that looks like is something like this. So on a plot of temperature versus daisy coverage, there's some temperature, which is at the moment 22.5 degrees, and then there's this window here. So if it's the way it's programmed in there is it's a parabola shape. So if it's too cold or too hot, then there won't be daisies. And then if it's very cold, but still in this window, then there'll be some. And the warmer it gets, the more daisies will grow. This is just the sort of the daisy preference for living. Okay, so on the left side here, we have this negative feedback that we drew earlier. Okay, so if the temperature goes up, so let's say we're here, temperature goes up, then more daisies are going to grow. Okay, that's what we have with this coupling here. But if we get past this line and the temperature goes up, the number of daisies decreases. So let's look at the model again. So 22.5, and then the peak temperatures that they can live at is 39, 40 degrees. Okay, but 22.5 is their favorite temperature. Okay, so the temperature with the white daisies is increasing until it crashes at about 30. And we can see up here, so when it got to 22.5 was about right around here, so 1.44 luminosity. And you can see here on this plot that, so the pink line is the percentage, so the blue line is the basically the number of daisies. So when it gets to 1.44, we can see that it flattens out. Okay, so that's the point where the daisies are hot enough that if it gets hotter, there's fewer of them. Okay, so that was like that's the 22.5 right there. It's like, all right, no more daisies are going to be growing or surviving in terms of like, I mean, they keep dying and growing, but the overall population isn't going to increase anymore. So that's the beginning of the end. Okay, and so now when we've switched over into the positive feedback loop here. So now every little bit hotter it gets, less and less daisies can live, and very quickly it gets to a point where it just completely falls apart. So on this side of the diagram, then we have a different feedback loop. We have the white daisies again, and we have the temperature. However, how's this going to be different? What I said was when the temperature increases now, less daisies are going to want to be there. So more temperature, less daisies. So this has become negative. And it still is the case, though, that the more white daisies there are, the more white daisies there are, the lower the temperature. So that hasn't changed. So the way that I was reading about feedback loops some more, and what they said was draw the arrows, and you always have to come back and walk around the loop. It doesn't matter where you start, and that's how you can really check. So two minuses would be a plus, but then let's check it. So let's say that the temperature, we're over here, the temperature increases because this is solar forcing. Temperature up, less white daisies. Less white daisies, temperature goes up. Okay, so that is, in fact, a positive loop. It's just causing the temperature to just go more and more up. If we're being forced, if the forcing is to increase the temperature. So we can summarize that here. Just say that the switch from stable, or actually let's be more careful with this. The switch from negative feedback loop to positive happens when the planet's temperature exceeds the optimal growth temperature of the daisies. So this information. So in order to really describe this system, we need more than just these feedback loops. We need this information about how daisies operate. So that's worth reminding ourselves. We need more than feedback loops. And that's been kind of apparent all along, right? Like there's a tendency, we're not quantitative with these things, right? You can imagine if, some of these dependencies might be very strong, some might be weaker. Oops. Okay, this diagram here can sort of help us think about this concept of stability. Let's imagine 2 points. We have a point A and a point B. Okay, so if you're at point A, it's a bit cooler. There's fewer daisies. If you're at point B, there's a lot more daisies, and it's quite a bit hotter. And I'd say intuitively, in terms of the stability of the system, if you could live on a planet at point A or point B, it's pretty obvious that A would be a better planet, right? Because if the climate changes, there's just a lot more leeway. I guess at point A you're a little close to getting freezing, but let's say we're not worried about that. We're more worried about it getting hotter. In that case, B is closer to this point where we're going to spin out of control. I guess if it got too cold, the daisies would die, but if it warmed up again, they'd come back. So that's not so bad. This is bad though. Switching over here where you're in this positive feedback loop. And roasting the planet. Don't want to do that. So let's just make note of that. So this diagram helps us see that point A is more stable than point B. And that's because we could survive a larger perturbation in temperature without switching to positive feedback. Okay, so then the question is basically what determines, how do we determine sort of where we are in one of these diagrams? So daisies, as far as daisies go, if you were a daisy and you were in charge of having the most daisies around, you'd actually, the most daisies occurs right at this tipping point, right between the two, right? So it's actually planet is probably better off if we're not at the sort of maximum amount of daisies. So it's not as if the daisies are deciding. That's simply Daisy's preference. Say it that way. We need to address like where we're going to be at a certain point on a diagram like this. We need another relationship, and that's the one relating the albedo and the temperature, independent of the daisies. So I'm gonna redraw that. Okay, so we got this plot of temperature, daisy coverage, and so this relationship here looks something like this. Okay, so we're not thinking about daisies. So actually, daisy coverage or albedo, right? Because those things are synonymous in this model. So if the planet's getting any given day a certain solar input. If that input is, well, say whatever that there is an input, okay, and if there's a high albedo on the planet, the temperature will be lower, right? Because a lot of that energy is being reflected off. If the albedo is low on the planet, the temperature will be higher because it'll be absorbed. Okay, so this graph, independent of daisies, but it has the same axes. So if we draw the daisies preference diagram onto there, we find intersection at 2 points. So this is like a graphical, it's a way of looking at, it's still a pretty simple system. And as systems get more complicated, even Daisy World is fairly complicated. We need math. We need differential equations to get numbers for these things. But we can look at them. We can look at them graphically, to sort of better understand what's happening. That's what we're doing here. So the two relationships that governing that relate temperature and albedo essentially are plotted here, and they intersect at 2 points. So let's call this point C, and call this point D. So C and D are what we call equilibrium points. And you might guess that when we're on this side of the negative feedback loop, this side of the positive. So C, you might guess, is the stable one. And D is unstable. We can picture this on the same sort of energy diagram. We had the surface with the marbles in it. So point C is in a depression. Point D. So we could imagine a marble here, and D would be like a marble here. So D is a point where if it's not going to, if everything operated perfectly, you could stay here. The temperature doesn't get any hotter or colder. The beta doesn't change. It's not going to go anywhere. But as soon as it gets a little cooler or a little hotter, it's going to roll that direction. So imagine, for example, we're over here. For some reason, it gets a little colder one day. More daisies are going to grow because the daisies like it when it's a little bit cooler than these temperatures. Their optimum is not in that direction. It's a little bit colder. The planet here, this relationship, when it gets let's see on this relationship here. Right, the planet. Well, this is between the planet and albedo, so let's not worry about that for the moment. It got colder, more daisies grew. That increases the albedo, right? Albedo goes up. It's going to get even colder. If we make it a little colder, it's going to head off this direction and head us back into but marble's going to roll down the hill, right, to get us to the other stable point. And as we talked about before, C is a stable point. If you're at point C and you get colder, you get less daisies, which decreases the albedo, right? And that's going to cause the planet to warm back up, which is going to give you more daisies back. And the same thing if you go up here, you're gonna end up kind of pointing back towards that point if you find yourself, due to some perturbation, off from the stability point. So this is some sort of energy. This is like, it's a thermodynamic. This kind of diagram appears a lot in when you're thinking about thermodynamics. So this kind of diagram describes why molecules are spaced apart at certain distances. All kinds of things. All kinds of systems sort of end up in these positions where they reduce some measure of energy is minimized. And the slopes and the heights, like on these diagrams, are meaningful. So, for example, the degree to which the slope is going to determine like how fast things move from one position to the other, or how big of a perturbance would knock you out of your stability point. So that's what we want to talk about next, and I'm going to switch to a different color. Try to here. Okay, so imagine that the solar flux at Daisy World increased. So this is what we showed in the model, right? This is what happens. It's getting hotter and hotter. Or sorry, it is getting hotter, but the main thing is that the solar flux is increasing steadily. So we call this a forcing. So what does that look like on a diagram like this? What it looks like is Oh, I didn't manage to change the color. There we go. But let's try blue. Okay, so blue. So this this line that we drew that represented the albedo temperature relationship, not considering daisies. So the blue line is for the hotter, or sorry, the higher solar flux situation. So why did that happen? Okay, so basically, so we forget about daisies and we just say, okay, if you're getting more, there's still going to be a relationship between albedo and the temperature of a planet, and it's going to have the same slope. So if your albedo is higher, you're going to have a lower temperature. But since the sun is getting brighter, for any given albedo that you might have, let's say you had an albedo of whatever value that is, in the old system that would correspond to a lower temperature, but when you're getting more input from the sun, it shifts to a higher temperature. So your albedo, let's say, is 0.3, right? On Earth, we're at some temperature. The sun gets a lot brighter. Even though we're 0.3, we're going to have a hotter planet. That's what we've done here with this blue line. So I'm going to erase that arrow just for now. You can see why we got there, and that defines a new stability point. Okay, this is point E, and as we talked about before, E is closer to this kind of tipping point. So what does that look like on a diagram in terms of energy? So E, you can see a couple things. For one thing, okay, on this higher solar flux planet, there's more daisies and the temperature is higher. And we're not getting into the math of this at all, but the other unstable equilibrium point, or the other equilibrium point which is unstable, is here. Okay, so this is E. We could, if you want to, we could call that F. Okay. And we're still on the same axis here. So as you can see from the topography here is that I've drawn this hill shorter, right? Because let's imagine the wind blows here. You're a lot closer to going off the edge. And as the planet gets hotter and hotter, this line is going to keep moving over to the point where there is no stable situation. So we don't really think the edge really isn't. You might look at this and think up here, you see this. Oh, it's like it's curving down again. But remember, if we were at a point like here, kind of between E and F, we're still on a slope where F, anything in here is going to head back towards E, right? But this distance between the two, right, that's getting smaller and smaller as the planet gets hotter. So what happens, this is sort of just writing down what we've been describing. What happens as solar flux increases in daisy world? So we do that. The albedo temperature relationship moves such that for any albedo, the temperature is higher. So that's what I just described here when I do that arrow indicating how this shifted. So that's because the sun is brighter. And I got to tell you, this material is in the reading this from the Comp book. I had to read this several times and think about it quite a bit before I could really wrap my mind around this stuff. So if you're feeling a little bit like we just kind of went to a different dimension, that's fine. I'm not surprised. This stuff is a little bit higher level than a lot of what we've been doing, but I think it's pretty cool. It's a very powerful approach to kind of get into this and thinking of it in terms of this sort of diagram with energy. It's more of a thermodynamics kind of approach. So these sorts of diagrams I'm familiar with originally from petrology class. So the same kind of thinking goes into what if you have a molten rock and it crystallizes, you form a granite, like which minerals form? Why does feldspar crystallize instead of amphibole or something? It has to do a lot with this kind of thing. You have these surfaces, and whichever phase has the lowest energy, that's the one that's going to appear. So that works for metallurgy and so this kind of thinking is pretty. If you haven't seen it before, it's pretty cool stuff that's kind of behind the scenes for a lot of things like freezing of water and boiling points and all that kind of stuff. Okay, so back here. So we're answering this question. What happens as solar flux increases in daisy world? Right, we do the blue line. So the system, bottom line is the system moves closer to instability. Eventually, there is no stable equilibrium. But before that, I guess we should say it becomes more susceptible. I'm not going to spell that properly. It becomes more prone to switch to a positive feedback due to disturbance. So this distance, in other words, this distance, let's just call it CD, is larger than EF. So as CD gets shorter, a nudge is riskier. I'm kind of writing the same thing more than once. So basically, right, if you bumped E, if you were here, you'd have to have a climate anomaly that pushed things way over here past D before the system would flip out. In this case, so going from C to D is a lot further than going from E to F. So if you manage to increase the temperature so much that you found yourself here, when the unstable, on this side of the unstable equilibrium, you're going to go off into, you're going to lose all your daisies and your planet's going to burn up. Right? Because a little bit hotter, less daisies, less albedo, hotter, less, you're in this positive feedback loop. So I hope that gives a glimpse of a little bit more what's going on in terms of, when you look at this model, a little better understanding of why did this switch? Why did this happen here? And what we showed was at the point where at 22.5 degrees, we got to this point where daisies stopped growing. They just leveled off because they don't like it any hotter than that. And that switched us at that point on this diagram. We're basically where this curve had moved even further to a point like there, right? Any more daisies? So this number of daisies is stable, right? So at this particular luminosity, which is at 1.45 or so, it's a stable point. But we're right. Instability is right there, and so as it gets a little bit hotter, this line goes off, right? And there is no stable point. And that's what we see happening here. So in a sense, you could just look at this and say, oh, yeah, at 22.5 degrees, and you could talk about, okay, at that point we switched to a positive feedback loop. That's an important observation that, in terms of like what's happening in this diagram. But I think there's something powerful about considering it from this perspective and kind of understanding the system of equations. So this diagram in these intersecting lines is a graphical way of visualizing the math that's going on behind the scenes and actually calculating for any particular combination of circumstances, what the temperature is going to be and how many daisies there are going to be, and then when it's going to switch.